Part 3 of Unit 7 is gas stoichiometry and the ideal gas law. In the last section you learned the molar volume of a gas. We said that at standard temperature and pressure, 1 mole of a gas has a volume of 22.4 liters. We can use that as a conversion factor in stoichiometry problems that are asking about volume at STP. So in this example, what volume of CO2 will be formed by the combustion of 5 grams of propane, C3H8, at standard temperature and pressure? We're working on this page. First thing we have to do is write our balanced equation. Propane is C3H8. It's a combustion reaction, so it has to react with O2, and it's going to form water and carbon dioxide. Now, we had 5 grams of propane, and it was asking us the volume of carbon dioxide that's going to be produced. We'll balance our equation, put a 3 here for the carbon, a 4 here for the hydrogen, and we'll put a 5 in front of oxygen. So now our equation's balanced. What we'll do is start with our 5 grams of propane. It's a stoichiometry problem, so the first thing we need to do is convert into moles. So we want to cancel out grams of propane and get to moles. So we'll use the molar mass of it. 1 mole of propane has a mass of 44 grams. So grams of propane is going to cancel out. Now we'll do the mole ratio between propane and carbon dioxide. For every 1 mole of propane, we're going to produce 3 moles of CO2. Now, typically, in stoichiometry problems that ask you to find the mass of product formed, we'd be going from moles of CO2 to grams using the molar mass. However, we're going to use our molar volume conversion factor because we know this reaction is taking place at standard temperature and pressure. We'll cancel out moles of carbon dioxide by saying that 1 mole of CO2 has a volume of 22.4 liters. So everything cancels out. 5 times 3 times 22.4 divided by 44. We do this, we end up with 7.64 liters of CO2. So that's how you use the molar volume of a gas as a conversion factor in a stoichiometry problem. We'll look at another example real quick. We'll look at this reaction of hydrogen and nitrogen reacting to form ammonia. And let's suppose that we had 2.5 liters of hydrogen and we want to find out the volume of ammonia that we can produce. Now, we'll start with the value that we were given, 2.5 liters of H2. And it's a stoichiometry problem, so we're going to convert into moles. And remember, this is all happening at STP, standard temperature and pressure. But we're going to convert to moles by using 22.4 liters per mole. 22.4 liters of hydrogen is 1 mole of H2. Now we'll do our mole ratio. For every 3 moles of H2, we produce 2 moles of NH3. So our liters have canceled out, moles of hydrogen is canceled out. And now we'll go from moles of NH3 to liters. 1 mole of NH3 has a volume of 22.4 liters. So when you solve this, it ends up being equal to 1.67 liters. Now, hopefully you noticed that, didn't we do this step pretty much twice? We did. At standard temperature and pressure, we can skip the mole ratio step and use what's called a volume ratio. We'll just treat the coefficients as liters. So we could have simplified our math in this one, started with 2.5 liters of hydrogen, and instead of converting to moles and do the mole ratio, we'll just use the coefficients as liters. For every 3 liters of hydrogen that we have, we produce 2 liters of ammonia. and our answer would still be 1.67. Now you can only do that for gases at standard temperature and pressure, remember. Before we go over problems that are not at STP, we need to learn about the ideal gas law. Ideal gases are imaginary gases that perfectly fit all of the assumptions of the kinetic molecular theory, which was an earlier video, and I've just kind of restated it here, so I'm not going to read it. You can pause and read it if you need to go back over it. But we need to remember that ideal gases don't actually exist. They're imaginary gases that we really wish perfectly fit all the assumptions of the kinetic molecular theory. The ideal gas law is PV equals nRT. In the ideal gas law, P equals pressure in atmospheres, V is volume in liters, N is moles of a gas, T is temperature in Kelvin, so we always have to convert Celsius to Kelvin for the ideal gas law. Same way we need to convert other units of pressure to atmospheres for the ideal gas law. And R is called the universal gas constant. R has a value of 0.0821, and it's got units that take, it combines the units of pressure, volume, moles, and temperature into one. So the units for R are liters times atmospheres divided by Kelvin times moles. So it's a complex unit, but it allows us to cancel out any other units when we're doing an algebra problem with the ideal gas law. So the ideal gas law can be used to solve algebraically for any of the four variables, P, V, N, and T. You're not going to have to solve for R because it's a constant. We know what it is all the time. So instead of using 22.4 liters per mole to go from volume to moles, we're going to use the ideal gas law when we're not at STP. You're going to plug everything in and solve for moles instead of using 22.4 liters per mole. So let's do an example with that. A 2-liter gas tank is filled with 5.5 atmospheres of acetylene at 35 degrees Celsius. How many grams of water vapor will be formed when it is completely combusted? Let's write our balanced equation. Write it up here. Acetylene is C2H4. It's a combustion reaction. To balance it, we need to put a 2 here for carbon, a 2 here for hydrogen, and a 3 in front of oxygen. So there's our balanced equation. And they've told us all the information about acetylene. We know the volume, we know the pressure, and we know the temperature. What we don't know is how many moles that is. Now, if it was at STP, we could use 22.4 liters per mole as a conversion factor. We can't here. We have to use the ideal gas law and solve for N, which will be our number of moles of acetylene. Then we can do the stoichiometry to figure out how many grams of water are going to be formed. So we're doing the ideal gas law first. So we're going to use PV equals nRT. Our pressure is 5.5 atmospheres. We have to convert our temperature from Celsius to Kelvin, except that's on the other side, my bad. 5.5 atmospheres times 2 liters. We're solving for N, the number of moles, multiply by our constant, 0.0821, and this is where we have to convert our temperature from Celsius to Kelvin. 35 plus 273 is going to be 308 Kelvin. So to solve for N, you just divide this side by 0.0821 times 308, and N turns out to be equal to 0.43 moles of acetylene, C2H4. Now we can do our stoichiometry to answer the question. I know we've done an equation, but we haven't answered the question yet. So we'll take our 0.43 moles. We'll do our mole ratio. For every 1 mole of acetylene, we produce 2 moles of water. And it's asking us for the mass of water, so we'll use the molar mass. 1 mole of water has a mass of 18 grams. So moles cancel out, and then the moles of water are going to cancel out. 0.43 times 2 times 18. Our answer to this question is 15.48 grams. So that's how we use the ideal gas law to find the moles of our starting substance before we did our stoichiometry. Your question for this section: a 20-liter container is filled with 500 grams of carbon dioxide. What is the pressure inside the container if the temperature is 22 degrees Celsius? You're not doing stoichiometry on this question.